Well, howdy. Welcome back to our series on DC electronics. This is going to be topic number 6. We're going to be talking about parallel circuit construction on your breadboard. We're going to talk about analysis of parallel circuits and as well as troubleshooting. So in this title page, you'll see I've got 2 multimeters on a parallel circuit, and I'm measuring current and voltage simultaneously. The circuit that we're going to be using is shown in the drawing of the cover sheet. I've got 3 resistors in parallel with each other. We will define how you recognize parallel components. And so I've got 3 resistors in parallel with each other with a 5-volt source. Let's go ahead with the next. Okay, let's go ahead and define what is parallel. My friends, listen carefully. Devices are electronically in parallel, and this is big, if and only if. Did you see that? If and only if. There's 2 conditions that have to exist. So the first condition of the if and only if is the leads on one side of these devices meet at one node. So do the top of these resistors meet at a connection point, which we will call a node? Yes or no? Yes. There's an and. The second condition must be satisfied. And that second condition is the leads on the other side of these devices have to meet at another node. So look at the illustration. Do the bottom leads of these resistors meet at a lower node, a lower connection point? And that is yes. So therefore, as I've illustrated, R1 and R2 are in parallel with each other, not just geometrically appearing to be in parallel with each other, but electronically in parallel with each other. So this is an if and only if statement. I'll repeat it because I'm one of the most redundant instructors that you'll come across. Devices are electronically in parallel if and only if the leads on one side of these devices meet at one node, which they do at the top, and the leads on the other side of these devices meet at another node, which they do at the bottom. So tip to the wise, as you've been continually journaling your information from these training videos, please do channel this into your journal. Next. All right, so let's go ahead and differentiate what is a tap, what is a node, and what is this phrase that I have in parentheses, electronically the same point. You'll see that phrase used many, many, many times in the vernacular of our electronics technology. But let's start off with the word node. Node is any point connecting 2 or more devices, okay? A node is a point connecting 2 or more electronic devices. You should record that into your journal. Tap. Tap is a digital multimeter connection point. It is the point at which we will analyze the circuit for a variety of considerations. It could be resistance, it could be voltage, it could be current, but they are connecting points for where a DMM can attach for us to evaluate a concept of interest at that tap. Then the third bullet point, this phrase, electrically the same point. This is a very common phrase. What does it mean? What it means is there are multiple connected nodes and taps with 0 ohm wires between them, okay? Electrically the same point. It's not a singular point, but it could be multiple connected nodes and taps as long as they're connected with 0 ohm wires between them. No devices. So let's go ahead and see how we clarify this. Here we go. So if you look at the illustration, I've got points A, B, C, D, E, and F illustrated in red type yellow backgrounds. So it says nodes, which I define as A, B, D, and E. Those points, point A, point B, point D, point E, are defined as nodes, and they're shown in the illustration as dark filled circles, okay? And as you can see, A and B connect the resistors at the top, D and E connect the resistors at the bottom. They are called nodes because they connect more than one thing. Taps, and I show C and F as being taps. They're defined as taps, and they are unfilled circles on schematics. Unfilled because those are going to be connection points for your digital multimeter. Now let's look at the phrase, electrically the same point. Points A, B, and C at the top are electrically the same point. What I mean by that is point A, point B, and tap C, point C, are they attached to each other with a 0 ohm wire? We'll consider all wires in our schematics to be 0 ohms. But we know that a physical wire may have some fractions of an ohm, but as far as our schematics are concerned, these wires are 0 ohms. So is point A, point B, and point C, are they attached, yes or no? They are. And how are they attached? They're attached with wires. Is there any component between A, B, and C, like a resistor or an LED? The answer is no. So if these points are connected with a wire, and presumably that's 0 ohms, that makes point A, point C, and point B electrically the same point. Now look the lower part of the illustration, points D, E, and F, are they also connected with a separate wire? The answer is yes. So point D, E, and F are considered to be electrically the same, even though points D and E are nodes and F is a tap. They're physically points that are connected together. They are considered to be electrically the same. This phrase will become significantly more important as we go on with future videos. Now, look at this last consideration. Points A, B, and C are separate from points D, E, and F. Okay? Those upper set of points are not electrically the same as the lower set of points. Okay, why? Because they're separated by R1 and R2. Okay, all right, let's go ahead to the next one. Now, parallel circuits, like series circuits we've studied before, have characteristics and they have formulas. So, word to the wise. Again, call to action is transfer this information into your journal, chronicle it so that you have it as a immediate reference when you need it. So what I've got is an illustration that shows on the upper left a parallel circuit with 3 resistors, 10K ohm, 2K ohm, 1K ohm with a 9-volt source. And it shows how the electrons flow out of the negative plate at the bottom of the 9-volt source and flows across to the right to the first resistor. Now at that point, the current splits at that node. So part of the current will come up through the 10K ohm resistor. The rest of the current will continue to the other 2 branches. The current that continues through will be split again at the bottom of R2. Some of the remaining current will go up through R2, and the rest of the current will go up through R3. At the top of the illustration, the currents flow back to the source. And so the first bullet point that we're going to state here is parallel circuits divide current and are called current dividers. That's the nickname for parallel circuits. So if you're talking about a current divider, you are talking about a parallel circuit. Parallel circuits, also nicknamed a bank. I may have discussed the nickname for series circuits previously. If you don't recall, the nickname for series circuits is a string. So a string of resistors are those that are sequentially one after another, like a string of pearls. So string is the nickname for series circuits, whereas a bank, B-A-N-K, is the nickname for parallel circuits. So second bullet point, voltage is the same across the branches of a parallel circuit. So each one of these, R1, R2, R3, represents a pathway, represents a branch by which the current can be split. So branches are the nickname for the pathways in a parallel circuit. Third bullet point, RT will always be less than the lowest ohmic branch. And we'll show you how to calculate this in a moment, but record this. Your lowest ohmic branch of these 3 is 1 kilo ohms. The total resistance of these 3 in parallel is not the sum of 10K, 2K, and 1K, giving you 11K. 11K is not the R total for this circuit. If I had these three resistors in series, then yes. Oh, sorry, 10 plus 2 plus 1 is 13K. So if I had these three resistors in series, then the total resistance in series would be 13K. But in parallel, the R total will be less than the lowest ohmic branch, which is the 1K ohm. And I'll show you how to calculate that later to prove to yourself with the formula in a moment. Next, the largest ohmic branch will flow the lowest current. So the 10K ohm resistor of these three being the largest ohmic branch, 10K compared to the other two, will have the lowest current, the most restricted path for current to flow. Whereas the next bullet point, the smallest ohmic branch, the 1K ohm resistor, has the least resistance. Therefore, it will allow the highest flow of current of the three branches. Next bullet point, currents are proportionally distributed through the parallel branches, which is a summation of the previous two bullet points. And then finally, the circuit will not be off if there is a break in one of the branches, much like the newer Christmas tree lights. In the old Christmas tree lights that you remember from Grandma's house, if one light bulb blew out, the whole string was off. Well, not so with parallel circuits. With parallel circuits, which is the way new Christmas tree lights, the newer Christmas tree lights are set up, if one bulb goes off, no problem. The rest of them are still on. So the circuit is on even though there's a break in one of the branches. So take a look at the illustration at the upper right. The upper right shows direction of current flow that seems to be contrary to our electron current flow that we've discussed before, and it is. It is called conventional current flow. Conventional current flow you'll find in your textbooks is the same as whole current, H-O-L-E, and it's a concept that was through literature, perhaps popularized by Benjamin Franklin. As Benjamin Franklin said, electricity travels from where there is higher potential to where there's low potential. So he, in the fable, had a kite in a rainstorm with a key, and then the lightning hit the kite in the sky during a rainy rainstorm event, and the electricity of the lightning traveled down the wet kite string and then hit the metal key at the bottom, and luckily he didn't die. Well, anyway, the current that flows from the positive side of the battery source through the three branches that go back to the negative side is the opposite direction of electron current flow. So for the rest of this discussion, for the next bunch of series of training videos, we will only be using electron current flow as a concept. We will not be talking about conventional current flow or whole current as illustrated in the upper right. But since the direction of flow definitely appears to be opposite of the illustration of flow of the diagram on the left, I thought I'd take a moment and explain the difference. Okay. We have some formulas, basic formulas, really simple. VT is equal to the voltage across branch 1 is equal to the voltage across branch 2, and however many branches you have. If you have 15 branches, then the voltage total is equal to the voltage of each branch. You'll see this mathematically and as well as on your circuit boards in a moment. Next formula, I total. Now, I total is different from the I total in series circuits. Here, I total is the sum of each of the branch currents. So the sum of the current through branch 1, branch 2, branch 3, they will add up to give you the total current. RT is really interesting. RT is shown with this formula that looks really intimidating, but it's really easy to calculate. And there's a separate slide that I'll have in a moment that explains why RT is calculated using this formula. Then there's also the power. So the total power of lamps dissipating energy in the form of heat and or light is calculated as branch 1 power plus branch 2 power, all the way up to however number of branches you have. Finally, as we previously had VDF, standing for voltage divider formula, for series circuits, In parallel circuits, we have CDF, which is current divider formula. And we'll talk about how to apply that later on, but you should transfer these concepts from this page into your journal. Next. All right, let's talk about why is RT in parallel less than the lowest ohmic branch. Here's why. Here's an excerpt from my electrical units table. And I've expanded it. I've taken away the power because it's not of consideration for this discussion today. But I've brought in the row that shows conductance. And G is the symbol for conductance. And conductance has 2 units. The European designation for conductance is in units of Siemens. Why is it in units of Siemens? Because look at the engineer, the scientist on the far right, Ernst Werner von Siemens, a German engineer. And if some of you might know, there's a very, very famous large conglomerate in Europe, electronics firm called Siemens Corporation. So 1 unit for conductance is called Siemens. Now, here in the States, we like to do things a little uniquely or different, and we use the units mhos, M-H-O. M-H-O is ohm spelled backwards. Did you see that? Ohm is O-H-M, whereas mho is M-H-O. So plural is mhos. And then the symbol for mhos is shown as an upside down omega. Okay, if the regular omega represents resistance, ohms, where an upside down omega represents mhos, which is the opposite of resistance, is called conductance. Look at the definition. The definition shows ease of the flow of electricity. It is the opposite of resistance. And if you look at the resistance row right above it, you'll see the formulas are converse of each other. R is equal to the reciprocal of G, meaning 1 divided by G, whereas G is the reciprocal of R, meaning G is equal to 1 divided by R. You'll see how we do these in your calculator in a moment. So how does this work? If you take a look at the colander on the upper right, colander, your food strainer that you'd use in your kitchen, if it only had one hole, it would have a limited amount of current flow. If it had 2 holes, then the amount of conductance increases, okay? So if we increase conductance by adding a hole, if we increase the G, then more current will flow, which is I, and if more current flows, then that will result in R being decreased. We'll calculate this in a moment, show you how easy this is. So the bullet points at the bottom, simple, why RT is less than the lowest ohmic branch. First of all, R is resistance. It is the opposition to current flow. Talk about that. G is the symbol for conductance, and it's equal to 1 divided by R, or the reciprocal of R. And what does G represent? Conductance represents the ease of current flow. In what units? In units of mhos, which is shown with the upside down omega, or Siemens, if you're in Europe, shown by the symbol capital S. Last bullet point, R and G are reciprocals of each other. What that means is if resistance increases, then conductance decreases. Whereas the last sentence here, if conductance increases, like the addition of a couple of holes, more flow, meaning conductance increases, then overall resistance must come down. That's why R will be always less than the lowest ohmic branch in a parallel arrangement. Now let's get into the weeds here. Here we go. If you remember Ohm's law says current is equal to V over R. And this nice picture of a colander shows a lot of different holes here. So let's go ahead to the bullet points. R is resistance, opposition to current flow. G is conductance, which is the reciprocal of R, which is the ease of current flow in units of mhos. Then imagine a colander capable of holding 5 pints of fluid and 1 hole representing 100 ohms of resistance. So if that 5 pints of fluid represented 5 volts and the 1 hole represents 100 ohms, do the math according to Ohm's law, 5 divided by 100, you will get 50 milliamps of current. Now, we're going to put in 2 holes. They're equal size holes. The resistance is 200, sorry, the resistance is 100 for each hole. They do not add. You do not have a total of 200 ohms here. What you have is another pathway for current to flow. What you have is greater conductance. So look at this fourth bullet point. It says now two equal size holes. That would represent 20 millimos of conductance, because previously 100 ohms represented 10 millimos of conductance. So now with two holes, we have 20 millimos of conductance. So how do I calculate R in this case? R is calculated as the reciprocal of G. So what is the reciprocal of 20 milli? It's 50 ohms. Two holes has now changed the resistance from 100 ohms down to 50. The resistance has gone down by half. If we've added a second hole, we have twice as much current flow, twice as much conductance. The resistance has now decreased. Overall resistance. Now, the last bullet point, 8 equal size holes, each one being 10 millimos of conductance. 8 of them represents 80 millimos of conductance. How do I calculate R? R is the reciprocal of G. You should say that. R is the reciprocal of G. Just you speak it, you write it out. Good for you. So this would equal to, R is equal to 1 over 80 millimos, which is now 12.5 ohms. So with 12.5 ohms divided into the 5 volts, what is my current now? 400 milliamps. Has the current gone up in each case? Has the resistance come down in each case as I keep on adding more holes? And if you look at the illustration on the bottom far right, tons of holes, lots more paths of current, way more current coming out of this 5-volt bowl of potential. And that means my overall resistance has increased down to very, very, very low. So conclusion, more branches equals more current. Okay, more branches equals more current. Now, next, we'll get into the nitty-gritty of some numbers here in a moment. Actually, it probably wouldn't hurt for us to do this right now. So what I'm going to do is I'm going to segue into my camera for just a moment and show you the calculations for this. So the bowl represents 5 volts of pressure, of being able to push fluid out of the bowl. And in each hole represents 100 ohms, which is equal to the R. We said that G is equal to 1 over R equals 1 over 100, which works out to be 10 millimos. So I'm going to use the upside down omega for the symbol for mos. And how do we derive that? Very simply, let's go ahead and hit clear. And so on the calculator, you just simply hit, you don't do a 1 divided by 100. That's going to slow you down. You're going to use the reciprocal key, which is this one here, x minus 1. So you key in 100. So I'm going to key in 100. So now I have 100. And I'm going to hit the reciprocal key. Boom. So it shows -1 up here. It's not a -1. It is it's a reciprocal function display. And then the moment I hit equals, it will do the calculation for me. It'll show me that I have 10 milli. Okay. So this will be 10 millimos. So now if we do this, now we put in 2 holes. 2 holes means I have twice as much conductance, twice as many. So this is equal to 20 millimos. So R is equal to 1 over G, which is now equal to 1 over 20 millimos. How do I key this R now? How do I key this into the calculator, the 20 milli? So clear the calculator, and this is very easy to do. We will go ahead and take 20. Now, how do I entered this as milli, I hit a shift and hit my milli function right here. So I've got milli, and then all I have to do here in order to do this reciprocal function is hit my reciprocal key, this 1 minus x, boom. Now I have 20 milli being reciprocated, and now if I hit equals, I have 50 ohms. This is what I'm looking for. So 50 ohms. So how does this compare with what we had originally? What we had originally was 100 ohms. By adding a second hole, current has increased, conductance has increased. What has happened to resistance? Resistance has gone down. It's now from 100 to 50. So that's why we would have a resistance decrease as we increase pathways in a parallel circuit. So more branches equals more current equals less resistance. So I'm going to do one more for you. All right, because in the previous slide we had 8 holes, yes? So 8 holes is equal to 8 times 10 millimos is equal to 80 millimos. So R is equal to, and we said that resistance was calculated as the reciprocal of G. So is equal to the reciprocal of 80 millimos. And so R is going to be calculated. And let's go ahead and do that. Pretty simple. Clear the calculator. And let's go ahead and enter 80 milli. So 80, and a milli with shift here. Milli, hit the reciprocal key right there. So do I have reciprocal of 80 milli on my display? The answer is yes. And then now I'm going to hit the equal key and take a look. How many ohms do I have? 12.5 ohms. Okay, so as you can see, mathematically, as we increased the current with one hole and the total resistance being 100 ohms, then we went to 2 holes. My resistance came down to 50 ohms by half. When we went to 3 holes, 3 pathways, 3 branches for current to flow, my conductance increased. My total resistance decreased even further. So that brings us to our conclusion of more branches equals less resistance. And okay, so in the yellow box, conclusion, more branches equals more current equals less resistance. All right, next. What's parallel, what's not parallel? And this is something that's really important for y'all to take a look at. If you take a look at the upper illustration, I have an R1, R2, and an R3. Are they in parallel? The answer is no. They are not in parallel. They are electrically not in parallel. R1 and R2 are electrically what? They are in series, okay? They only appear to be geometrically in parallel, but they are not in parallel electronically. Take a look at the lower illustration. Here, R1, R2, and R3 are electrically in parallel with each other. Why? Do the upper leads connect together at the top of the circuit? The answer is yes. Do the lower leads connect to another point separate of the upper wires? Do they connect at the lower part of the circuit? The answer is yes. So the definition of parallel that I gave you earlier, if 2 or more devices have leads on one side connecting to one point, and then the leads on the other side, meaning the bottom side of these resistors, they connect to a separate point, then they are truly in parallel with each other. So these 2 illustrations may help you differentiate the upper circuit as being geometrically, they look like they're in parallel with each other, but electronically, R1, R2, R3 in the upper diagram are in series, whereas the lower circuit follows the definition that I gave you earlier for parallel relationships. Next, circuit building tips. Oh, this is huge. All right, we talked about this in a previous training video. Avoid spaghetti wiring. Okay, please avoid spaghetti wiring. When you start off as a babe in the woods for building your electronic circuits, yes, you're not shown anything better, so you walk around in diapers, and yes, you end up with spaghetti wiring. Spaghetti wiring it makes it very difficult for you to plan things out, carefully troubleshoot, and allow classmates to look at your circuit builds and understand what it is that you've built. So my recommendation is, rather than use spaghetti wiring, let's go ahead and use neat wiring. And I showed you some illustrations of neat wiring previously. How do we achieve this? First of all, trim your resistors. The resistors that you use as they come out of your resistor packets should be bent and trimmed, cut short, so that the leads, the axial leads coming out of the sides of the resistors will give you enough length, consistent length, such that you could use a mini hook and grab onto the top axial lead right there. And then the trimming of this is roughly just barely half an inch. It's really about 11.5 millimeters. But if you cut it to half an inch, that'll work out just fine. So by trimming them to half an inch, it will allow the resistors to go fully onto the board, but yet stick up just enough so that you could put a little mini hook for a probe onto the side of the lead of the resistor. So here, the bend allows for a connection of the mini hook to the left and right sides of the resistor as they come directly out of the resistor, or you can also connect it on the down post of the resistor. This is easy to do, and you only do a few at a time. Now, if we take a look at the illustration that I have on the right, it'll show you a contrast between the resistors that come standard in your kit. They're really good resistors. They happen to be precision resistors, metal film resistors, which means they're only plus or minus 1% error. But the ones that come in your kit are smaller, and the wires are very fine and can lead to, if you use spaghetti wiring, a lot of bent wires and some inconsistent results. My recommendation is, if you can, since I have bigger hands and I'm a little clumsier with very fine components with these hammy fingers, I like physically larger resistors with wires that are more stout, so they're not as likely to crumple like what you're going to get with spaghetti wiring. So let's talk about neat wiring with trimmed resistors and solderless jumper wires, okay? So first of all, let's go ahead and differentiate the kinds of resistors that you might have in your lab at your school. Very often, a lot of schools use these that are shown on the far left. They are carbon film resistors. They're very inexpensive. And a 1/2 watt carbon film resistor has a tolerance or a margin of error that's plus or minus 5%. Try to avoid these unless it's absolutely necessary. Try to stay with the metal film resistors because their tolerance or their margin of error at 1% gives you more consistent results that match your calculations. So I have two different metal film resistors that are shown in this upper illustration. The one that comes in your kit are 1/4 watt, meaning they will dissipate up to 250 milliwatts of heat before they potentially burn out. Whereas the 1/2 watt resistors, you take a look at the metal film resistor here in the middle, that's a 1/2 watt metal film, and that's quite a bit larger than the ones that come in your basic kit. And take a look at the lead. The lead is substantially more stout than what comes with the 1/4 watt metal film resistor. So this makes it much easier to handle. So my recommendation is with metal film, 1/2 watt, which will certainly be within the plus or minus 1% tolerance. Now, if you take a look at the illustration on the right, it's a nice resistor pack that I discovered on Amazon. And what's really nice about this is it does show you really nice examples of the color banding that's appropriate for each of these values. And so if you haven't learned your color resistor bands and how to do color coding of your resistors by now, I'll discuss that briefly in the next slide. But it's nice in this packet that they are compartmentalized with the specific amount of ohms and the color banding, and each compartment is latchable so that they will not spill out. So physically, if you look at what you have, also these, as they're in here, are not held together with masking tape, so you don't have to worry about removing the schmutz that you do with the resistor packets that are bound by masking tape. So let's talk a little bit about your color coding. Here we go. My friend, Professor Nabil Al-Hamal at Chabot College, had put together these color coding engineering prefix and symbols charts. And they're really handy. They're in the form of plastic laminated cards. And they're really, really handy as a quick reference for your color coding, as well as engineering prefixes, as well as symbols for the different electronic units, the symbols, the units, and the units for the symbols. Now, what I have shown in the upper left is the resistor packs and another illustration of the three resistors side by side. So I won't get into the details of how we are going to use the Ohm's law chart, how we're going to use the resistor color chart. All that's covered in your textbook and in your lectures with your professor, but it's nice to have all of this in one place. And let's just go ahead and do this. Sorry for that silence in that transition. Anyway, what we have, if you do decide to get the resistor pack, let me show you them in detail. I have rubber bands around them because, like your jumper wires, if you don't put rubber band around this, if this opens up and it spills out into a million pieces, you're going to cry the big tear. So in each one of these, I put the rubber band around them, and then they come as a set like so, and goes into your bookshelf very, very easily. You just slide out the range that you need. And what's also nice about this is if I go to take off the color band, take off the rubber band and open up, say, the 1K ohm resistor, it is shown with the appropriate color banding for you. See if I can bring this up where you can see this a little better. 1K shows the appropriate color code for a 1K ohm resistor, a 1.5, 2.2. So the color banding is represented here. And then if I go to open this up, unclip, I have all my resistors in place right inside, like so. And they're easy to retrieve and use as you need. So each compartment has 20 resistors, and you have quite a range of different resistors that you are likely going to want to use for the more advanced circuits that we will be getting into by having quite a bit more selection of resistors than what normally would come with your basic kit. So I recommend this for two reasons. Number one, they're physically larger than the standard resistors, and they're easier to handle. All right, next. All right, so as we go from this slide, Professor Al-Hamal's useful, friendly charts, we will get into parallel circuit building. Let's go ahead and construct these on our breadboards. And how's that done? Again, we're going to use the neat method. We're not going to use spaghetti wires. And using the neat method, what it is that we have are the resistors. If you look at the three resistors, I have them in the same sequence as in the schematic, 100 ohms, 220, and 330 left to right. And I also happen to have the tops of each of these three resistors connected to the same point. In other words, all the top of the three of these is connected to the red rail. So the top of these resistors being connected to a common point by itself does not mean they're parallel. What has to happen? The lower leads also have to be connected together to a different common point. So if you look at the pathway for R1, red rail down to row 25, I get a jumper between 25 on one side to 24 on this side, yellow jumper wire from 24 to the blue rail. I'm repeating that wiring for each of the three, what we call branches. So I have three branches that are in parallel with each other. And then the jumper wires, the brown jumper wires are here to allow for me to quickly pop in three LEDs. The three LEDs we've used before, not for measurements, but really just to check our pathways to make sure something is not awry with how we've wired things. So, troubleshooting question. Here we go. You've built this. And once you've built this, you pop in your three LEDs. After popping in your three LEDs, you light this up with your power supply, and only two LEDs light up. Two of three LEDs light up. One doesn't light up. Troubleshoot this. What is a possible cause? What is a possible cause that would cause one LED not to light up? Think, think, think. Troubleshooting question. Because this is likely to happen for several reasons. First reason, LED might be backwards. Remember, the LED is polarized. So if the LED is but backwards, you've got to find that LED and pull it out, the one that's not lit, flip it around, stick it back in the circuit, and hopefully if that was the singular cause for the LED not lighting, then presumably the LED will light. Next troubleshooting question. The LED that doesn't light, three of them are supposed to light as shown. One does not light. What do you do? Well, you did the LED flip. You took the LED out, you flipped it around 180 degrees, you stuck it back in the circuit. It still does not light. The other two are lit, but this third path is not lit. What could be wrong? Well, think about that. Pause, 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 pause. Yeah, you're right. One possibility is we may not have continuity in that path. So for example, if you look at the upper left illustration, my resistor, that third resistor, which is supposed to be in this case on row 15, might be on row 16 or row 14. It might be one row off from where my brown jumper is connected. Or my brown jumper may have one pin off from where the resistor is connected. Or I might have a misconnection down here between the brown jumper and the lower yellow wire. Or I might have a missed connection for the lower lead of the yellow jumper to the blue rail. So any misconnection here, here, or here could lead to the third LED not lighting up. Here's another thought. You may have trimmed your resistors too short. Instead of the resistors being trimmed at roughly ½ an inch, you might have it trimmed at something much less, and therefore one of the ends of the third resistor might not be going entirely into the socket of the breadboard. And the same thing is true for these jumper wires. If these jumper wires are bent upwards or something, that could be another possibility. So several possibilities for the third LED not lighting up in your troubleshooting questions. One was what? Flip the LED. Second, check your connections if that LED still does not light up. All right. Didn't know you were going to get quizzed, did you? Ha. All right. So now let's go ahead to the next one. All right. So what we're going to do is we're going to break out to our video and show you this in greater detail. Actually, breaking out to the video at this point in time might not be as useful because these photos are just like really, really sharp. But yeah, let's go ahead just for a moment and break this out. And do this. Okay, this should be huge on your screen. So I've got the 100, the 220, and the 330 ohm resistor in place. The 100 ohm is connected to the red rail, 220s to the red rail, 330s to the red rail. So they are connected at the top. And then I have the resistors connected to brown jumpers, and the brown jumpers then connected to yellow jumpers to the blue rail. So this forms three different branches. I've got one branch here, another branch here, and another branch here, all flowing electricity from my power supply, blue rail, all the way up through the red rail at the top. Okay. Another illustration shown. Let's go ahead and flip it around this way so you can see it from a slightly different perspective. So from this perspective, you can see with the leads cut and trimmed the way that I have it, the leads will allow for connection of your mini hooks like that. Okay. And they're high enough off the board that I can also connect the mini hook to the vertical side lead of the resistor like that. Okay. So that is a close-up of how the resistors actually sit on the board, and you'll appreciate the neat wiring method as we move on. So let's go ahead and do this. All right, let's move to the next slide. Next slide goes to show, click. All right, how do we calculate this? You look at this formula and it looks really intimidating. Not a problem. I'll show you in a moment with your calculator keystrokes how easy this is. But let's look at the illustrations. I've got taps and I've got nodes identified in both of the illustrations. I've got the formula shown at the top for upper left for any number of resistors. So our total is equal to the reciprocal of three, the sum of three reciprocals. Reciprocal of R1 plus reciprocal of R2 plus the reciprocal of Rn, where n represents the last branch that you might have. So if it's like 10 resistors you have in parallel, then this would be all the way out to R1, all the way out to R10. Here in the illustration that I have on the right, I have two resistors, R1, R2. And so the formula goes reciprocal total resistance is going to be calculated this way, is going to be the sum of the reciprocal of R1 plus reciprocal of R2. Total resistance is 1/6 plus 1/12, and that's equal to 3/12, 3/12. If I reciprocate that, meaning flip them numerator to denominator, denominator to numerator, 12/3 gives you 4 ohms. That's a lot of words. Let me show you more easier way to understand this. Let's go ahead and take a look at your calculator. You got to look for these buttons. Now, on some calculators, the button is designated as X-1. On some other calculators, it's designated as 1 divided by X. They both are the same function. They just designated a little differently graphically on the calculator, depending upon whether it's a Casio, Sharp, brand X, brand Y, Hewlett-Packard, Sony, whatever. Different manufacturers like using one and some like using the other. So find the one that is on your calculator and we can do this together. So I'm going to give you 3 resistors in the first scenario, 20 ohms, R2 is 40 ohms, and 30 ohms. So our total for these 3 in parallel, now these are in parallel, not in series. You don't add these up. This is not 20 plus 40 plus 30 giving you 90 ohms. No, no, no. Remember, our total has to be less than the lowest ohmic branch. What's the smallest branch of these 3? 20 ohms. So our total has got to calculate to be less than 20 ohms. If you calculate something close to 20 or something more than 20, take a moment and recalculate. It doesn't take but just a moment. It's pretty fast. And so how do we do this with your calculator? We do this with your calculator as 1, hit your reciprocal key. Remember, your reciprocal key is one of these 2 that are shown here. I'm using this illustration, X-1. So 20 reciprocal will give us the 1/20. And I'm going to add it to 40 reciprocal, which gives me the plus 1/40. And I'm going to add it to 30 reciprocal, which gives me the plus 1 over 30. And then I'm going to hit equals, which basically closes the parentheses of my sentence. And then once I hit the equals, I have to hit reciprocal one more time and then hit equals one more time, and I will get 9.23. Is 9.23 ohms lower than the smallest ohmic branch of 20? The answer is yes. If I do this, another example, I have three resistors, 980 parallel with 470 parallel with 680. How do I do this on the calculator? Never mind about all of this math written out. On the calculator, it's really simple. You just take the first set of ohms, 980, hit your reciprocal key, plus, don't forget the plus, 470, hit the reciprocal key, plus 680, hit your reciprocal key, then followed by equals. Then you have to hit reciprocal one more time in order to calculate 216.51. Why do we have to hit reciprocal one more time? Well, look at the big formula on the upper left. Big formula on the upper left. Does it not show in the denominator, open parentheses, reciprocal of R1, add with reciprocal of R2, add with reciprocal of R3, close parentheses, and this whole denominator is going to be divided back into one, or in other words, it's going to be reciprocated one last time. So R1 reciprocal plus R2 reciprocal plus R3 reciprocal equals, takes care of this parentheses, and then you hit reciprocal one more time, it takes care of the 1 over to give you equals R total. All right, we're now going to do this on the calculator, show you how easy this is, okay? Let's go ahead and do this. Pause here. Okay, we should be looking at my camera screen, and what it is that we wanted to start off with. I wanted to show you the double vertical lines that represents a parallel function. So you would read this as R1 parallel with R2 parallel with R3 equals what total? And so the three resistances that we were given in the previous slide was 20 ohms in parallel with 40 ohms in parallel with 30 ohms. And the way you put this into your calculator, as was shown, was simply 20, and then you hit your reciprocal key. This is your X -1 key. Then you add. What are you going to add it to? The next 40, and then hit your reciprocal key again, and you're going to add. What are you going to add that to? 30, hit your reciprocal key one more time. Okay, now after the 30 ohms, you're not going to hit add anymore because you want to close out the denominator. Remember, all this was in parentheses, and then all of this was divided into 1. So you're going to hit equals. Then X -1 one more time and hit equals one more time. And let's go ahead and do this on your calculator. Okay. Turn the puppy on. And very simply, let's go ahead and start with the first one. 20, and here's your reciprocal key, X -1. See X -1 right there, yes? And if it's not X -1, it could be 1/X on your calculator, but this one is an X -1. So what I'm going to do is I keyed in 20, I'm going to hit reciprocal, and it shows up on my calculator as 20 -1. And then I'm going to add to the next 40 reciprocal, and then add, got to hit the add button, 30, hit the reciprocal. Now, after this reciprocal, I do not hit add. What do I have? I have to hit equals, which closes my parentheses. So equals. And after I hit the equals, then what do I need to do? Hit the reciprocal key one more time. Boom. And then what do I have to hit last? Is my equal function. Boom. And guess what? I end up with my 9.23 ohms, which is what we had calculated earlier. So let me write this out. This is equal to 9.23 ohms. Right there. Okay, okay. Next, let's do this one more time because we had another example. We had 980 in parallel with, what do we have? 470 in parallel with 680. So my RT, remember our total, is the reciprocal of 1 over 980 plus 1 over 470 plus 1 over 680, close parentheses. So what we're going to do is we're going to do the bottom first. We're going to do the denominator of this fraction first. 980 reciprocal plus 470 reciprocal plus 680 reciprocal equals, hit reciprocal one more time, equals my RT. Watch how this works. It's really quite elegant. Put this up here so you can see this a little better and clear the calculator. All right, so I'm going to do my 980, so 980 right there. I'm going to hit my reciprocal key, add 470, hit my reciprocal key, add 680. Once I added the 680, I have to hit reciprocal. What happens after reciprocal? I do not hit add. There's nothing else to add after the 680. I have to close this with an equal sign. Equals. So I've calculated my entire denominator. Now I have to reciprocate that, bring that, complete the calculation of it being under a 1. So I hit the reciprocal key one more time and then hit equals one last time. And lo and behold, we end up with the number that we had shown previously, 216.51 ohms. Now remember, we round off consistently to 2 digits after the decimal point. So your answers and my answers will be spot on, matching each other. You don't write out all the rest of those digits. Okay, so let's see how we did. Well, lo and behold, guys and gals, yes, 9.28 ohms was what we had calculated first go around. And yes, it was, in fact, lower than the lowest ohmic branch of 20 ohms. Second time we calculated the next set, we had an R total of 216.51 ohms. And yes, it is in fact lower than the lowest ohmic branch of these three. It is less than the 470 ohms. So that's proof mathematically on your calculator that RT is in fact less than the lowest ohmic branch. Now, let's go ahead and look at a circuit and where all these numbers work out and how we end up with these currents, okay? Okay, so our total, I'm showing this using the double vertical lines, is equal to R1 in parallel with R2 parallel with R3. So R1 is 100 ohms in parallel with 220 ohms in parallel with 330 ohms, and that's 56.9 ohms. Easy to do. We'll do that in a moment. You can take a moment and write this out also. Based on Ohm's law, how do we calculate I total? I total is calculated as V total divided by R total. Well, my V total is 5 volts. My R total is 56.9 ohms. So if I do the math, I'll end up with 87.87 milliamps. Nice. That's my total current. Now I'm going to use current divider formula, CDF. Current divider formula is very elegant, like voltage divider formula was for series circuits. Current divider formula allows us to very quickly determine branch currents. As long as we know R total, we calculate it. As long as we can calculate I total, then we can see how this circuit will divide current between the three branches. Mathematically, it's very simple. So if we take a look at IR1, current through the first branch, using this formula, it's in parentheses, R total divided by Rx. So if I want to calculate the current for first branch, I would use the R total of the circuit divide by R1 of the first branch equals, and then times my current total. So in this case, 56.9 divided by 100, 56.9 is my R total, divide by 100, which is my R1, right over here, R1's 100 ohms, and then multiply by 87.87 milli, I get 50 milliamps. Next, if I want the current through R2, then the only thing that changes in the formula, RT divide by R2. RT is still 56.9 ohms, but I'm dividing by a new denominator now. Instead of dividing by 100, I'm dividing by 220, which is the value of my R2. Multiply by total current, and this current divider will chunk out 22.73 milliamps for the second branch. And then the third branch calculates to be 15.15 milliamps. So a couple of things here. Let's take a moment and notice this. Which one of these branches has the highest current? IR1. 50 milliamps is far more than these other two branches. What did we say earlier? Didn't we say earlier, and from your journal you should have this noted, that the lowest ohmic branch will have the highest current? Which one of these is the lowest ohmic branch? R1, it's only 100 ohms. Does it, in fact, have the highest current? Is IR1 the highest current of the three? Yep. Then we said conversely, the highest ohmic branch of the three, in this case, the 330 ohms, will have the lowest current flow. And that's IR3. And is that, in fact, the lowest current flow? Yep. Sure enough, it is. Yes, sirree. Now, we just calculated these using Ohm's law and this current divider formula. Let's see what the simulator cranked out. The simulator program showed I've inserted ammeter 1 for the first branch, ammeter 2 for the second branch, ammeter 3 for the third branch, ammeter 4 for total current, meaning all these currents coming back to the source. So it shows for ammeter number 1 for the first branch, hey, check this out, 50 milliamps. We calculated 50. The sim program shows 50 milliamps. Ammeter number 2 for the second branch, it shows it should be 22.73. We calculated 22.73 milliamps. The third branch, the sim shows 15.15 milliamps for the third branch through ammeter number 3, which is through resistor number 3. We calculated 15.15 milliamps. And then how about the total? The total going back to the source is the sum of all of these. And ammeter number 4 shows the total current should be at 87.88 milliamps. What did we calculate? 87.87 milliamps. We're not going to sweat bullets for the 100th of a decimal point. It's pretty much right on. In other words, the sim program is using a slightly different rounding technique than we are. But if we're within 100th or a couple hundredths of a decimal point, we're really happy. Okay, so total current is great. And if you take a look at the branch currents, IR1 is designated as branch current for 1, measured between points 5 and 1. So let's say I took out the points on this, so we won't be able to see this. But anyway, first branch current is 50 milliamps, second is 22.73 milliamps, third is 15.15 milliamps. Let's see how we do this on the calculator. Okay. And we're going to maybe do one more here before we go to calculations. Yeah, results from the sim program verifies my voltage across all of the resistors at 5 volts apiece, verifies my currents as through the 4 ammeters, and verifies my branch currents as shown. All right, so now I'm going to go ahead and go to calculations. Hopefully you have the current divider formula written in your journal. So let's go ahead and do some of these, okay? Okay, let's take a look and see what we have, my friends. We have CDF for current divider formula. Current divider formula is given as IRX, the unknown resistor, is equal to, in parentheses, our total divided by that particular resistor value times total current. So we have to start back with RT. RT for 100 parallel with 220 parallel with 330, that calculates this way. Remember, we will have clear, and we will do 100, clear, 100 reciprocal plus 220 reciprocal plus 330 reciprocal equals reciprocal one more time equals was our 56.90 ohms. 56, we round that 56.90 ohms. So equals RT equals 56.90 omegas. My I total is equal to V total over R total, which is equal to 5 volts over my 56.9 ohms. And so this works out to be, let's go ahead and move this over a little bit here. Clear? 5 divided by 56.9, yes? So 56.9 equals, and I have 87.87 milli. Now, you might not have a prefix calculator. Yours would show 10-3. And if it shows 10-3, then you're going to need to go to your handy dandy engineering prefix chart and know that it's supposed to be milli. But anyway, we will have IT is equal to 87.87 milliamps. All right, that's my IT. So now if I want to apply current divider formula for IR1, IR1 is equal to R total over RX. So it's equal to my R total of 56.90 over my R1, which is 100, and then multiply by 87.87 milliamps. And so my IR1 will calculate to be, don't want to have my cap dry out or my pen dry out because I don't put on the cap. Clear? All right, so take 56.9 and divide by my 100. I could hit equals or not. Yeah, algebra works just fine on the calculator, times 87.87, and my milli is presented as shift milli equals. And guess what? The 49.998, how would you round? Milli works out to be what? Pretty darn close to our calculated 50 milliamps, which is what we calculated earlier. So using the same technique, we should be able to verify the other currents of IR2 of 22.73 milliamps and IR3, which would be calculated as 15.15 milliamps. And does I total equal to IR1 plus IR2 plus IR3. And you'll find, yay, lo and behold, they do add up to be the 87.87 milliamps that we had calculated using Ohm's law. Cool. Next. Okay, so we just finished verifying the calculations. Let's go on. All right, so making measurements of V, I, and R, measuring voltage, measuring resistance. We'll talk about that and demonstrate this in just a moment. Let's go ahead and see what the ohmmeter looks like when we go to connect in order to measure voltage and resistance. Current will show separately. So right here, this goes to show the connection for measuring total resistance. I'm going to use jumper wires, jumper wire attached to the blue rail to one of my hooks, and an orange jumper to the red rail attached to the other hook. And you say, well, wait a minute, Co. Why do I have the black hook of my ohmmeter attached to the red rail? Why do I have the red mini hook attached to the blue rail? Aren't these opposite of each other? The answer is no. Remember, measuring resistance is not polarity sensitive. Resistors have no polarity. So when I'm measuring resistors singularly or as a group, it doesn't matter which red or black goes on which side of the resistances. In any case, we did calculate total resistance to be 56.9 ohms, and I'm measuring 57.2, which is again within a margin of error that's acceptable for a number of reasons. I have some resistance within the board itself. I have some resistances of the wires. And so as long as we're pretty close to the calculated 56.9, and that's reasonably close, we're happy campers for these guys to be measuring our total in parallel. And now it's very important when you go to do this that the power supply is removed. See, the power supply here cannot be on the board when you're measuring R total. If the power supply is left on the board, you will not be able to measure anything close to the desired resistance. So in order to measure total resistance, you have to remove the power supply. Next, measuring voltages. Measuring voltages, you have to put on the power supply. You have to turn the puppy on, and you can go measure with your hooks or your needle probes and attach to either side of each resistor. I'm not going to do that here, but you've done it, or you should do it on your circuit board and check, are you close to 5 volts? Now, remember, these power supplies are not rock solid 100% at 5.00. Some might be slightly more, some might be slightly less. Are you close to the 5-volt output that is predicted for your power supply? The answer here shows it's 4.98. We're pretty darn happy. Yeah, that's close. Next, measuring currents. Now, this requires a bit more work. Remember, you have to break the circuit open. Where did I break the circuit open? In this case, I removed the first jumper. By removing the first jumper, I have created an open right here. And by creating an open, that's where the ammeter leads must go. The red hook must go to the more positive side of the open, and the black hook or probe must go to the more negative side of the open. The open is only here. Do not connect your probes anywhere else other than where the brown jumper used to be. Is this set on milliamps, and does it show us something pretty darn close to 50 milliamps? I have measured 49.8 milliamps. It's pretty darn close to the 50. Separately, I happen to have a separate multimeter attaching this to show that I've got 5 volts DC across the resistors. Okay, and interesting to note here, I'm not using a USB for power. I'm using a 9-volt battery with battery clips onto a barrel connector. And what I like about this is it reduces the number of heavy cables across my workbench and makes this board completely portable with a 9-volt battery and a barrel connector. There's a link to that, as well as a link to the resistor packs in the Amazon affiliates that are at the end of the YouTube. Next, how do I determine current number 2? To determine current number 2 through this branch, I have to rebuild the jumper in the first branch. I cannot leave this open and just yank out the brown jumper for the second branch. I have to rebuild this, yank the second jumper, and then measure across here. Watch what happens. First jumper has been repositioned, so I still have current flowing through that first branch. The second jumper is removed, creating an open in my second branch. Connect the red lead to the positive side of the open, black lead to the negative side of the open, and I'm measuring 22.90. We calculated 22 and change for the second current, and yes, we are spot on. Now, next, in order to measure the third branch current, what I need to do, I need to rebuild the second branch and then pull out this last jumper to create an open on the last branch. Take a look. Are my first and second jumpers in place? Is my third jumper and only the third jumper removed? I can only have one place in the circuit open at a time when I'm measuring for current. So I've created the open here, and now I'm measuring something pretty close to my calculated we calculated 15.15 milliamps, and this is showing 15.17 milliamps, which with these metal film resistors, precision resistors, giving us pretty consistent results, which is great. Voltage is still 5 volts, and notice my connection points are slightly different. Red hook is still on the voltmeter on the positive side of R3, whereas the black wire is somewhere on the blue rail. And it don't matter where on the blue rail it is. Remember, everything on the blue rail is one common point. They are connected with nothing but wires, so it makes a hook up the black hook here, hook up the black hook here. Doesn't make any difference for my voltmeter. It's a happy camper showing us we've got a solid 5 volts. How do I measure total current? Well, I'm going to have to physically change this circuit, because if you look at the original circuit that I have on the left, there is no single point, none, that I can break open singularly in order to stick my amp meter in. I've got 3 separate branches hooked up to the blue rail separately. So what I'm going to need to do is to rebuild this slightly. It's easy to do. Take a look at my illustration in the middle of the screen. I have the three resistors in parallel with each other, and they clearly are for this reason. The upper lead of the resistors are all connected to the red rail. The lower lead of all of these resistors are connected together by these orange jumpers. The orange jumpers connect R3 to R2, R2 to R1. So that makes the lower leads connected to a separate point from the upper leads that makes all three of these in parallel. So I've maintained the parallel relationship, but by building it this way, I create a leg that comes down to my blue rail. So this is my singular path to ground. And so in order to measure this current, I'm going to yank this brown jumper wire, which I have in the third illustration, put in my ammeters. I'm using probes in this case. I interchange it between the mini hooks and the probes. And I have the regular probes in place. And as you can see, there is my 86.7 milliamps. Now, truth be told, we did calculate 87.7 milliamps. Again, we're not going to sweat bullets for a fraction of a milliamp or a milliamp in this case. We're reasonably close to the 87.87. We're happy campers. And I total is now measured. Yay. So let's go ahead and review some questions for understanding. Do the three branch currents add close to the 87.87 milliamps? Yes or no? You did the math earlier. Should be a yes. Does the largest ohmic branch, in fact, flow the lowest current? You analyzed this earlier. That should be a yes. Does the smallest ohmic branch flow the highest current? You answered this earlier. The answer should be yes. Very important you log this into your journal as very important points that have been proven in your calculations as well as your measurements. Now, on to more neat circuitry. This is an alternative layout for parallel circuits. And this layout is, again, very similar to the schematic. I've got my voltage source on the left, and I've got three resistors that are parallel to each other, but built differently. Why? Because this allows multiple points for measuring different quantities that I want to measure without having to reconstruct majorly any portion of the circuit. First of all, look carefully. Top of the resistors, R1, R2, R3. Oops, come back here, sorry. Top of the resistors, are they connected on row 12 in my board? Yes, they are. They're jumpered together with this brown jumper, but they are all connected to row 12. Are they separated with this blue jumper from the red rail? Yes, this blue jumper represents a potential for me to pull out, create an open at the top of the bank. Remember, a nickname for a parallel circuit is bank. So if I pull the blue jumper at the top, I have a potential point at which I can measure total current. Now, take a look at the bottom of these resistors. The bottom of R1 through the brown jumper is hooked up to row 20. Row 20 through this brown jumper is hooked up to row 20 on the right-hand side. And is the middle resistor connected to row 20? Yes. Is the third resistor through a shorter jumper also connected to row 20? Yes. Be very careful when you build this. When you build this, make sure R2 and R3 at this juncture are not on the same row. They can be on the same row at row 20, but these leads here, one is on 17 or this one's on 18, they have to be on separate rows at this particular part of our circuit build. And you'll see why later. It allows this jumper, the brown jumper, to be pulled for a current through R2 only. And then the current through R3 can be measured by pulling the blue jumper. I have one more blue jumper at the bottom. This blue jumper at the bottom allows me to make a connection point for measuring total current the bottom of the bank. So study this carefully. Try building it. R1 is 100 ohms. The second one is 220. Third one is 330. It's the same set of three resistors in a different arrangement. And I challenge you to do this. You do this at home. You don't do this at school because this is very time consuming. So let's go ahead and see how we do. We're going to want to measure total resistance. And as you can see in the upper illustration, no power supply is attached. I'm attaching red to the red rail, blue to the blue rail, and I'm measuring to total resistance, and it is at 57.1, which is close to my calculated 56.9. Again, we're not going to sweat fractions of an ohm, but pretty darn good. And I'm going to measure and you should measure each of these resistors separately before you even put them on the board. Troubleshooting question. What happens if you don't measure 57.1 or something close to 56.9 ohms? What do? Freak out? No. Troubleshoot. Think. Troubleshooting question. Remember, this is a big part of this particular video, is a lot of troubleshooting questions. What happens if you don't measure 57 or something close to 57 ohms? Maybe you selected the wrong resistors. Maybe you don't have a 100 ohm resistor in here when it's supposed to be 100 ohms. Maybe you don't have a 220. Maybe you don't have a 330. They could be the wrong ones. Did you measure them individually before putting them on the board? Hopefully so. If you did, and you're confident these are the right resistor values, then you want to check your board connections. Are your board connections solid where they ought to be? In other words, if you look at this closely here from the previous slide, are they all matching electrically to make the proper connections like so? If they're not, one pin might be off in the wrong position, and that means one resistor is not connected properly. You will not be able to measure the total resistance as you desire. So that would be your solution for troubleshooting. Make sure you have the right resistor values and make sure the circuit is built properly. Next, measure your voltages. And the voltages we did early, and you can measure across each of these directly from your on power supply. And yes, they should be something close to 5 volts. Now, measuring current is going to be a little more special. Measuring current, like we did earlier, you have to break open a jumper from the first resistor. And I removed the first jumper wire, which was between 17 and 20. So you remove first brown jumper from 1720, connect the ammeter to the open, and I'm using needle probes in this moment. And guess what? Something close to 50 milliamps. Is this close to our calculated 50 milliamps? The answer is yes. Now, to measure IR2, so you fill in the number up here and you answer yes or no down here. IR2. To measure IR2, you have to rebuild this jumper for the first resistor. If you don't rebuild the jumper for the first resistor, you're not going to get the 22.91 milliamps. No way. So what I'm doing here is remove the second jumper. So it says directions. In order to find the measurement for R2, I have to replace the first jumper, remove the second brown jumper, and then connect the ammeter to the open. And does this measure close to? Yes, it does. 22 milliamps is pretty darn close to our calculated value. And how do I measure the R3? Same idea. Replace the jumper for R2, remove the blue jumper wire, the shorter jumper wire that I had at row 18 to row 20, and that will allow me to create an open between these 2 points, put my ammeter, see, milliammeter function, put my ammeter here between these 2 points, verify I have something close to 15.15 milliamps, and I do. 15.16 milliamps is pretty sweet. Next, we're going to confirm total current, and total current is, I could do this one of 2 places. I said, in order to measure total current, you do have to replace that blue jumper wire here. You got to rebuild the current path for R3. And I removed the blue jumper wire in the lower portion of the circuit, created an open here, and stuck in my ammeter probes. And yes, I'm getting something not far away from the 87 milliamps that we had calculated. I'm happy with the 86.7 milliamps. Is there another place where you can measure this total current? I said yes. The other place where you can measure total current is by making sure the blue, oops, come back here, sorry. Making sure, come back here, sorry. Okay, making sure that the blue jumper up here is removed while the blue jumper down here is rebuilt, and I create another open up here. So I can measure total current through the removal of the upper blue jumper or the lower blue jumper. Either one will allow me to measure total current. Question, another troubleshooting question. What happens if you don't get something close to 87 milliamps? You freak out. You get nothing. Wow. Well, maybe your power supply isn't on. No, it's on. Maybe your power supply is not connected properly on the board. It is. Maybe one of these resistors is missing a connection that's properly not where it should be. Very possible. Because at this point in time, you've gotten all the other measurements, but this last one's not coming out. Maybe you didn't rebuild one of the jumpers. Perhaps you went to remove this one, and in your haste, you forgot to put the blue jumper back here, right? These are all troubleshooting considerations. Now, here's another troubleshooting question. What happens if your ammeter shows you nothing? It's on. It's on. You've got everything built. Power supply is on. Power supply is connected properly. All the resistors are in the right place. All the wires are in the right place. You go to hook up and it shows you nothing. What's the problem? Troubleshoot, troubleshoot, troubleshoot. Think, think, think. You're right. You may have blown the fuse. It can happen. It happens to me once in a while if I'm not paying attention. But it's okay. Luckily, you have a handful of fuses from the pack that I recommended that you acquire earlier. And if you didn't, you don't all have to have individual packs. Perhaps you can order one pack and share the 10 fuses or however many fuses you get and share with a couple of classmates. But in any case, spare fuses just in case the thing pops a fuse. And that would be one other reason why this would show you a nothing. So let's go ahead here. Parallel circuits, we want to confirm these. And again, it wouldn't hurt to jot these in your journal, all right? Because these are your conclusions. Is voltage the same across the branches of a parallel circuit? You measure this, you confirm this. Should be a yes. Second bullet point, RT is always less than the lowest ohmic branch. You confirm this on hopefully 2 circuit builds. Hopefully you built this first one and you built the advanced one. Is it less? The answer is yes. And mathematically, we showed you why, and also with the colanders, I graphically showed you why. Third bullet point, parallel circuits divide current and are called current dividers. Yes, the total current was around 87 milliamps, and part of that was chunked out through the first branch, part of that was chunked out across through the second branch, and part of that was chunked out through, divided, if you will, through the third branch. Next bullet point, did the largest ohmic branch in fact flow the lowest current? Yes, it did. Did the smallest ohmic branch, in fact, flow the highest current? Yes, it did. So very important conclusions that you should make. Next, troubleshooting questions. Number 1, I asked a bunch of troubleshooting questions all along this video, but here officially is one for you to think about because you're going to compare your answers to solutions that will be discussed at the end of topic 7 video, and that's coming up in a couple of days. So here's the challenge. So what if RT doesn't measure close to the calculated 57.2 ohms? We discussed some of those possibilities before. Well, what might you measure? Well, maybe R3 is not connected. So if R3 is not connected, then you want to calculate what R1, R2 calculates to be. Make that calculation. And then disconnect R3 momentarily and see if you measure this. And by the same token, suppose in number C, suppose R2 is not connected, leaving only R1 and R3 connected. What will those ohms calculate to be? That's a challenge troubleshooting question. Next, if R1 is not in the circuit for whatever reason, calculate R2 parallel with R3. What are those ohms? So what can you conclude why RT is not close to the 57.2 ohms? You need to answer that question. And we will review your answers to these questions in topic number 7 training video. Oops, here. Next, troubleshooting question, another one. Compare your answers to the solutions discussed. Oh, well, we're going to compare these in the next video, but what are the questions? It says, okay, what if I total doesn't measure close to the calculated 87.87 milliamps? I kind of touched on this in the previous slides as to some possible scenarios, but to help you along, do these calculations, because if one of the resistors is not in place properly, what could the current measure out to be instead of 87.87 milliamps? It would likely be one of these currents that you're going to calculate, or maybe total. We'll find out. So final question here is, what can you conclude why RT is not 57.2 ohms? Think about that. Jot your answers down. Next. All right. Your solutions for the previous voltage divider challenge analysis, number 1, back in the previous topic 5 video, and your solutions for the challenge design and analysis number 2 in the previous topic 5 video, plus these 2 troubleshooting questions in our topic 6 video, troubleshooting questions number 1 and number 2, all 4 solutions will be offered in a separate topic 7 YouTube. Okay. I choose not to at this point in time because this one's pretty long. I don't want to make this any longer than necessary. I will leave out the challenge questions for topic 5 to topic 7 video, and then topic 6 challenge questions here we will also discuss in the topic 7 video. So that's forthcoming. I'll generate that over the weekend and we'll see how we compare notes. So don't wait for my solutions and compare your nothings to my solutions and then calculate. You should calculate first, make your predictions, make your assumptions, write them down in your journal, and then we'll compare in topic 7 video and see how we come along. All right. Well, hopefully these videos have been helpful to you in your academic journey. Hopefully with this particular video, as we've gone through many troubleshooting questions and many troubleshooting scenarios, gives you hopefully a greater depth of understanding of what we're doing and trying to learn in the circuit building and calculation processes. And if you find these helpful in any way, please do give a thumbs up. That helps YouTube channel more questions and people searching for some of these helpful videos. It channels more people to this particular channel. And then if you would like to be informed of announcements of future videos as they come up, then certainly hit subscribe. It costs you nothing to do the thumbs up or subscribe. And if you like some of the accessories that I've shown in all of these videos, the links to these will be at the Amazon affiliate links, where you can click on and get directly to the items that I recommended. Costs you nothing more than the regular Amazon website. It is a regular Amazon website, but it just comes through this channel, and it helps to support this channel in being able to make more of these videos. So with that, my friends, I bid you adieu. Have a most wonderful, blessed, and we're coming into 4th of July tomorrow. That's when this video is created, on the 3rd of July. So I wish you all a safe and blessed holiday, and we will chat again in topic 7. Thank you very much. Koguy signing out. Cheers.